So this is a continuation of homework 8, and we're going to continue with problem 4, where we have a trampoline artist who jumps vertically from a height 2 meters above the trampoline. And we're told he jumps up and comes down and lands on the trampoline. And we're given his initial speed, so his initial position y1 is 2 meters, and his initial speed at this point here is 5 meters per second. And we asked to find in part A his speed when he reaches the trampoline, which is located at y is equal to 0. Alright, so to find the speed when he reaches the point here, we don't have to worry about what his energy is at this point. We can find his energy at his initial position when he starts off with a speed of 5 meters per second, and compare that with his energy when he reaches the bottom. So at the top here, his kinetic energy will be half mv1 squared plus his initial potential energy, which is mgy1, and this should be equal to this energy when it reaches the bottom. But at the point where he touches the trampoline, his y coordinate is 0, so you only have kinetic energy at the point where he touches the trampoline. Alright, so we have to solve for V2. So V2 will be equal to the square root of 2 times gy1 plus v1 squared, which comes out to be 8.01 meters per second. In the second part of the problem, so part B, we are told that he lands on the trampoline and then the trampoline is depressed So the trampoline is depressed by some distance. So when it's depressed, you have a new y3. So that's y2, and this is y3 when it's depressed. And at this point, he completely stops. So his v3 should be equal to 0. And we have to find what the how far he's depressed, so that we actually find y3 when the trampoline is depressed when he lands on it. So for part B, we can consider the energy, compare the energy at y3 to any of these, either a y1 or y2. But for simplicity, let's go ahead and compare it with y2, the energy at y2. So at this point here, his energy is completely the kinetic energy. And this should be equal to the energy at y3. So we write that as half mv3 squared plus his potential energy mgy3 plus the elastic potential energy of the trampoline, since it's part of the system. So this would be plus half k y3 squared. Okay. So in the problem, we actually ignore very small changes in the gravitational potential energy, since it's being depressed by a very small amount in the trampoline. So that means that we can set this part here to be equal to 0. And so now we can solve for y3. And we also know that his speed when it's completely depressed is equal to 0 because he comes to rest. So this part of the equation also goes to 0. So we end up with an expression which shows that his kinetic energy is completely converted into the elastic potential energy of the trampoline. So y3 comes out to be the square root of mv2 squared divided by the spring constant, which comes out to be 0.294 meters. All right, so the next problem involves number 5 involves a ball of mass 0.5 kilograms, so 0.4 kilograms, which is thrown upwards at some angle 30 degrees to the horizontal. So we know it's going to follow a parabolic trajectory, and we asked to find the speed at the highest point if we are given the initial speed v1 to be 11 meters per second. All right, so we know from earlier on when we talked about 2D kinematics that at the highest point, the y component vy is equal to 0, and there will only be an x component of his speed. And the x component of the speed here will be the same as the x component of his speed to start with, so vx, since there is no acceleration in the x direction. So for part A, the speed at the highest point will be vx, so we'll call that v2. So v2 will be equal to vx, which will be equal to v times the cosine of 30 degrees. So the final speed at this point here will come up to be 9.53 meters per second. And the second part asks us to find how high he's going to go given the conservation of energy. So we asked to find this height h. So if we set the y is equal to 0 to be this point here, then the y is equal to h will be the final position. And again, we can compare the energy at this point to the energy at the highest point of this motion. So to do that, at the bottom here, he's only going to have kinetic energy since his y coordinate is 0. So at the bottom, we have half m v1 squared being equal to his energy at the top, which would be half mv2 squared plus mg times his height. So we solve for the height, and so the height comes up to be, so the masses do cancel out, and the height comes up to be v1 squared minus v2 squared divided by 2 times the acceleration due to gravity, which is equal to 1.54 meters. Okay. So question number 6 has to do with a roller coaster, which is at different points, at different heights above the ground. So we're told that it initially starts from this point here, which has a height, so we call that y1, of 35 meters. And we're told that it starts from rest, so v1 is equal to 0. And we asked to find the speed of the roller coaster at a couple of other points. So point number 2, so y2 is equal to 22 meters. And we have to find v2. And when he gets to another point up here, number 3, where y3 is equal to so in the diagram you have in your books, this dips all the way down. So his y2 in this case is 0, and his y3 is 22 meters. So we have to find v3, and his final height at this point here y4 is 9 meters. And we have to find the speed at this point, number 4. Right, so for each of these points here, all we have to do is compare his energy with his potential energy at the highest point where he starts from rest. So for point 2, we can compare his potential energy up here, so mgy1, to his potential energy or kinetic energy when it reaches the minimum where y is equal to 0. So this would be half mv2 squared plus mgy2, where y2 is equal to 0, so we can cancel out the potential energy. So for his first point here, his speed at this v2 should be simply equal to 2 times g times y1, and the square root of that gives us v2. So his v2 is equal to 26.2 meters per second. Alright, so to find his speed at v3 and v4, we can do the same thing, compare his initial potential energy to his mechanical energy at these 2 points, and that enables us to find his speed at v3 and his speed at point number 4. So the next problem, number 7, has to do with an object which moves from some origin to position A, and then position C, and also to position B. And we are asked to find the work done in going from position OA, from O to A, and then A to C. All right, so we'll start off by drawing our vector here representing the force due to gravity. So the work done going from O to A to C should be equal to the work done going from O to A plus the work done going from A to C. And so the work done going from O to A is equal to the force due to gravity times the distance between O and A times the cosine of the angle between the force due to gravity and the displacement vector. So since they point in opposite directions, the angle is 180 degrees. And so the work done going from O to A comes up to be minus mg doA. And the negative sign here is because of the cosine of 180 degrees. Now we can find the work done going from A to C. And so this is also equal to the force due to gravity times the distance between A and C times the cosine of the angle between vectors AC and the weight. And since the angle between these two is 90 degrees, we have 90 degrees here, and the cosine of 90 degrees is 0. So the contribution of the work done going from A to C is equal to 0. So now to find the work done going from O to A to C, we just have to sum up these two values here. So the work done going from O to A plus the work done going from A to C is simply equal to minus mg doA. So in part B and C, we have to find the work done going along different paths, and we find out that they all come up to be minus mg doA, because the change in the potential energy only depends on the vertical distance or the height, the change in the height of the object from some reference position. Right. So for problem number 8, we're given that a box So we're told that the box starts off with some initial velocity vi, and it hits a spring and it compresses the spring some distance x, c, and we are asked to find the distance which the spring is compressed to bring the box to a complete rest. So in this problem, we're given the mass of the box to be 5.8 kilograms. We're given the spring constant to be 2,700 newtons per meter. And we're given the initial speed of the box to be 2.6 meters per second. Alright, so we can compare the energy at this point to the energy at the final position. So the initial energy, in the initial state, the spring is uncompressed, so all the energy will be possessed by the kinetic energy of the box. So on this side of the equation, we'll have half mv1 squared should be equal to, so once the spring is compressed, its final, the final velocity of the box v2 is equal to 0. So there will be no kinetic energy of the box, and we only have to consider the elastic potential energy of the spring, which is half kx c squared. Alright, so we just solve here, we're trying to find xc. So we find that the xc is equal to the square root of, so the halves cancel out, mv1 squared divided by the spring constant, which comes up to be 0.12 meters. Okay, so problem number 9 is a variation of the previous problem, except that we now have the box sliding down an inclined plane. Alright, so this time the box starts off from this height, and it compresses the spring by some distance xc. And so we're asked to find the distance the spring is compressed in this particular case if the box is brought to a complete rest at the end. So in this problem, we're given the inclined plane angle to be 36 degrees, and we are told that the spring constant K is equal to 2 times 10 to the 4 newtons per meter. The mass of the box is 12 kilograms. And it slides down a distance of 3 meters along the inclined plane. So the distance between this position and I apologize, along the inclined plane before it comes to rest is 3 meters. Alright, so we actually find the compression of the spring. And so in this case, we'll have to find at the beginning we're told that it slides from rest, so its initial velocity is 0. So its potential energy at the top will be equal to half mg times h. And that will have to be equal to the potential energy at the bottom of the box plus the potential energy of the spring as a result of its compression. So at the bottom of the ramp, we know if we set a y is equal to 0 to be where the box finally comes to rest, the y is equal to h will be where it starts from. So at the bottom, since y is equal to 0, there will be no potential energy of the box, and we only have the elastic potential energy of the spring, which will be half k times x squared. Alright, so in this problem we're not given the height, but we know what the angle between of the incline is, 36 degrees. So we know that the sine of 36 degrees is the height divided by this hypotenuse. So the height of the box initially is equal to 3 times the sine of 36 degrees. So we can put this height back into this equation and solve for the displacement x. So x comes to be equal to 2 times the mass times the acceleration due to gravity times 3 sine 36 degrees divided by the spring constant. And because x is square, we have to take the square root of this to give us this displacement, which comes up to be 0.144 meters.